Okay, what we want to look at now is we're going to, for it again, we've done in other cases, we're going to take a box. We're going to have a box on a surface, and we're going to attach a rope, and we're going to have somebody pulling on that rope. And so the idea is that there's going to be a force of pull on the block from the person that's tugging on the rope. And what we want to do now is we want to include friction on the surface. So whenever friction acts, the force of friction will act on an object. It always opposes the motion of the object. So now we're going to look at the frictional force on our system when we're pulling. And we'll have our normal force, and we'll have the force of gravity as well. Now what makes friction interesting as a force is the frictional force itself. The frictional force itself is actually made up of two things. It's made up of this thing called mu, and this mu, the Greek letter mu, is called the coefficient of friction. And the coefficient of friction is simply a number that's determined experimentally between two materials in contact. And the idea is that you only know that number, the coefficient, because you've experimentally put two different types of materials in contact, and as you experimentally tested them, you found this mu value for the friction. And it's basically, it arises from the atomic interactions between the two materials that are in contact. So you'll always see the coefficient of friction for like some type of wood and a metal, or rubber in the concrete, or rubber and blacktop, or something like that. There's always, it's the coefficient of friction between two types of materials. And then N, or as we should probably call it, I should be calling it the force norm. So let's switch this over here. So the frictional force is mu times the normal force, which we'll call N. Continue with our trying to standardize our labeling methods. So mu is a coefficient of friction. It's just a property between the property of two materials in contact, and the normal force. Now another thing about the frictional force is, as you can see, it shouldn't be equals. Technically, it should be the frictional force is less than or equal to. It's less than or equal to that value. So what do I mean by that? So the idea is, if I'm sitting here pulling on my block, and there's a force of friction between the block and my system. Well, the force of friction will match the force of my pull up until some value, and then so this on the x-axis, this is the force of my pull, and it's increasing going this way. The force of friction will increase up until mu Fn. So once you hit mu Fn, and you continue pulling, the force of friction doesn't grow anymore, and your force can continue to increase past it. And once your force of your pull is larger than this mu Fn, then you've overcome friction, and your object starts to experience that acceleration improvement. So mu Fn represents, this is how much friction can back work against you. Up until your force matching this, mu Fn will match you point for point. So when you think of summing your forces, you have the force of your pull minus the force of your pull minus the force of will match you to maintain zero to keep you in equilibrium up until the value of mu Fn. Once the force of your pull is larger than mu Fn, so if the force of your pull is larger than mu Fn, then you have some MA. So then you have some, because this number is no longer zero, this number will be some positive number then. So let's write if this thing, if the force of the pull is larger than zero, then you have some net force and you have an acceleration. Otherwise, up until that number, you're pulling on the block and it's not moving. You're like, and friction is matching your pull up until that value. Now it also turns out that there's two types of friction that are available. There's mu static, which is before the object moves. And then there's also something called mu kinetic. So this is static, and this is kinetic. And static is like when the object is sitting there and it's at rest, and then you have to come up and push on it to get it to start moving. And kinetic is once it's moving. And the idea is that the kinetic friction is slightly smaller than the static friction. So like you come up to the object and you start pushing and pushing and pushing on it. And finally you push hard enough and it starts to move. And once it starts to move, it turns out that mu k is a little bit lower than us, and that's why once you get that object to move, you don't feel as though you have to push as hard anymore to keep it moving, because it turns out that mu k, the kinetic friction, is slightly smaller than the static, so you don't need as large a force to keep it moving. Okay, so that's enough background, hopefully, on the force of friction. Now let's continue to look at our pulling on the box. Okay. So when we're going to pull on our box, what's going to happen? Well, we need to now look at the sum of our forces. So when we sum the forces in the y, okay, let's sum the forces in the y, and that's going to equal a1, as it always does. So when we sum the forces in the y, we have the normal force and gravity. So we have force normal minus force gravity equals MAY. As usual, we're going to say AY is 0 because our box is in equilibrium. So that tells us that the normal force is equal to gravitational force. So our normal force is the value of mg. And this is important now. Knowing the normal force is important because when we want to look at friction, we said that friction depends on our normal force. So now let's look at the sum of the forces in the x direction. So when we sum the forces in the x direction, that equals max. And what forces do we have in the x direction? Well, now we have forces. We have the force of our pull minus the frictional force equals max. So what happens? As I was mentioning before, we can plug in our terms. We have the force of our pull minus mu Fn, and Fn is mg, so we have this mu times m times g equals max. So what we see is if the force of our pull isn't larger than the frictional force, as we mentioned before, if Fp isn't larger than this number, Ax is 0 and the object, the box, won't move. But if Fp is larger than this number, then the box experiences an acceleration. And the acceleration, Ax, is going to be Fp minus mu mg over the mass of the object. So the idea is that Ax is going to experience an acceleration if Fp is larger than mu mg. And the difference, how much ever larger, will determine the acceleration of the blocks, of the box, whatever you want to call it, or the blocks. The combination of the block and box. So Ft, if this number is larger than this, even if it's just a slight bit larger, you'll have some small acceleration and the box will start moving. If it isn't larger than mg, the box will sit there because the friction force matches your pull up to that value. So it's important when we introduce friction into the system, it's a good thing that you always sum the forces in the y, because now you need to know the normal force in order to calculate the friction force to study the motion in the x direction. So this was our pull when it was horizontal to the surface, so we attach it when it was perpendicular to the surface. Now we want to look again at this friction force, but now we want to change the condition where instead of attaching our thing to the middle, we want to attach it so we're pulling up at some angle theta. And when we're pulling up at some angle on the rope, we have the force of our pull, but that is, we now have a force triangle, so we have to break the force of our pull, Fp, needs to be broken into F, this would be your Fpy, Fpx. We're going to say that Fpy is the Fp times the side of our angle, and Fpx is Fp cosine of the angle. So we have Fpy and Fpx. So we have to break our force of our pulls. We're pulling up on trying to pull up on the box and get it to move. We break our force of our pull into its components because it needs to be broken into x and y. Now, we still have, as always, the normal force working up, force of gravity down, and friction working against us. So let's look at the sum of the forces in the y. So when we sum the forces in the y, we have the normal force, we have the force of our pull in the y is up, part of our force of the pull is pointing up, and then we have gravity always working, and that's equal to MAY. But as we've always been stating for a while in these types of problems, AY is equal to 0, we're in equilibrium. So the normal force plus the force of my pull in the y minus the force of gravity is equal to 0. And this tells us that the normal force is the force of gravity minus the force of the pull in the y, which is now mg minus Fp sine theta. So our box, the normal force isn't working as hard this time because we are, by us pulling up on the box, we're reducing the amount that the normal force, how much weight the normal force has to provide to match the box. Now let's look at the sum of the forces in the x. So when we sum the forces in the x, we get AX. So when we look at the forces in the x, we have two. We have the force of the pull in the x minus the frictional force is equal to MAX. So when we look at this, we again see we have the force of the pull times the cosine of theta minus mu times the force of the friction times the normal force. Sorry about that. Times the normal force. And we said that the normal force is this, mg minus force cosine theta. So it's mg minus Fp sine theta. And this is going to be equal to MAX. So if the force of our pull times the cosine of our angle is larger than this friction piece, we're able to accelerate the box. Now notice that by us pulling slightly up on an angle on the box, we've actually reduced the normal force, which in turn makes the frictional force a little bit smaller. So it makes it easier for us to move the box, get the box moving. So as long as this piece is larger than the friction piece, the box will experience the acceleration in the x direction. Okay, but the thing to notice is that we've reduced the weight of the box, by a little bit by adjusting the force of our pull. So now let's do the last case where we can attach and pull on the box down. So this time we'll kind of preserve that so I'm not behind anything. So this time let's assume that we attach the thing higher on the box, and you're going to have some forces to pull down. And so you're like the third person and you attach it high and you're pulling it down. Well, when we're pulling down, we said that what we want to do is we want to define that angle theta there. Even if you're given this one, you want to come back and use this angle because that enables us to keep, and this is the force of our pull, and this becomes force of the pull sine theta and force of the pull cosine theta. And this is our FPX, and this is FPY. But you need to be careful when using theta because they may give you this angle here, and then you just need to make sure you turn it over and calculate that angle. So if they give you this angle, you just take 90 minus this angle to get that angle. But just be wary you need to keep this angle in mind. Okay, so now that we've broken our force of our pull into the components, now we can look at what's kind of going on. So let's start with summing the forces as we do in the y. So we sum the forces in the y, and that gives MAY. So what forces do we have in the y? We have the normal force. We now subtract the force of the pull in the y, and we subtract the gravitational force. And that gives us MAY. So these three forces are the sum of our forces, and we're equal to MAY. The box is in equilibrium in the y, so AY is 0. So the normal force minus the force of the pull minus FG equals 0. This tells us that the normal force is equal to the force of the gravity plus the force of the pull in the y, and this is mg plus FG sine theta. So we can see now the normal force has got to work a little harder because we're pulling down on the box. So what does that do for us in the x? The sum of the forces in the x is MAX. We have two forces in the x. We have our pull, FP. So the sum of the forces in the x is FPX minus the frictional force is equal to MAX. So when we're looking at this, what we have is we have the force of our pull in the x is FP cosine theta minus the frictional force, which will be mu, times normal force here, which is that mg plus FP sine theta equals MAX. So if our force of our pull is larger than this frictional force, which is now slightly larger because we're pulling down on the box, we've increased the normal force. If the force of our pull is larger than this, the box will experience an acceleration in the x. If we're not pulling hard enough, the box will just sit there and we're getting a good workout. So we've looked at three cases with friction this time on pulling a block. We looked at when we pulled it horizontally, we looked at if we were pulling up, and we looked at pulling down. So when you pull up, you reduce the normal force a little bit, and you reduce the frictional force, therefore, as well. When you pull down on the block, you increase the normal force a little, therefore increasing the frictional force. So just remember that the frictional force always opposes our motion, and it has this value of up to UFN. And so if your pull is larger than that frictional force, you'll experience an acceleration in x. If it isn't that large, then the object doesn't move because the frictional force won't match it. It's not that you plug this UFN directly in here, and then you'd say, oh, well, my frictional force is larger than this, it's some negative number. The frictional force only acts to oppose the motion. The frictional force itself doesn't cause like if you're pulling on the block and then suddenly the friction force starts accelerating the block backwards behind you, it doesn't work that way. It just will oppose up to the force that's being applied against it.